Yes, hello. I hope you're doing well. Man, Dennis Maximus back with A-level physics. And we are still looking at section B, the thermal properties of matter, or call it heat. This is the second lesson, labeled B002. Just to review a few of the questions that we looked at previously, I left with you questions where I asked you, number one, I asked you to explain the extent to which two thermometers based on different thermometric properties or different properties, but calibrated using the same fixed points, are likely to agree when used to measure. The first point was near one of the fixed points, and then the second point asking you to which extent will they agree if you are measuring temperatures midway between the two fixed points. Now understand that thermometers, actually, I'm going to start by answering number two, and then we go back to number one. Number two says, explain why thermometers may give different values for the same unknown temperature. Why different thermometers? Why do they give different values of temperature for the same unknown temperature? The reason is here. So different thermometers may give different values of the same unknown temperature because, the reason is down here, because they use different thermometric properties. That's the first marking point. They use different thermometric properties which do not agree or do not keep in step as temperature changes. Now, it doesn't mean that they keep in step as they are varying. They don't vary in the same way. They don't vary in the same way. They don't keep in step during their variation with the temperature. So please note this, that the different thermometric properties do not keep in step as temperature changes. However, the different thermometers are likely to agree at the fixed points because all of them were calibrated using those fixed points. There should be an S here, please, you put it there. And now that is the answer for number two. For number one, you were asked to explain the extent to which two thermometers based on different thermometric properties or different properties, but calibrated using the same fixed points, are likely to agree when used to measure temperatures near one of the fixed points. Because these thermometers, we just said, look at the answer for number two. And then you will understand how to answer the first point here. I should have called this Roman 1. So the different thermometers may give different values of the same unknown temperature, but they will be closely related, or they will tend to agree if you are measuring temperatures near one of the fixed points. Why? Because at the fixed points, the thermometers all agree. They agree at the fixed points. But midway between the two fixed points, you'll find that the midway between the two fixed points, that's where the greatest discrepancy or disagreement, I should say, arises. That's where you'll find a very big deviation. So when we are measuring midway between the two fixed points, we expect them to disagree to the largest extent. Why? Because midway between the two fixed points is the point which is farthest from each of the fixed points. Remember, agreement only occurs at the fixed points. I'm going to explain more about these concepts when we look at the different types of thermometers. But understand that if we are measuring, if you look at the fixed points, we said here, look at this. Different thermometers are likely to agree at the fixed points because they were all calibrated using those fixed points. So at the fixed points, they all measure the same temperature. But then as you go further away from the fixed points, you'll find that they start measuring different temperatures of the same object. So there will be a deviation. Why? The reason is because they don't keep in step. If you are looking at the thermometric properties, do not keep in step as the temperature changes. You may find that exactly midway between the two fixed points, you'll have the greatest deviation. The greatest difference or the greatest disagreement occurs midway between the two fixed points. And the reason is because midway between the two fixed points is the point which is farthest from each of the fixed points. And remember, agreement only occurs at the fixed points. All right. I want us now to proceed. And we close this. Now, today I want to explore what we call liquid in glass thermometers. Usually I should have put something here. Liquid in glass thermometers. Liquid in glass thermometers. So you can put liquid in glass like that. Hyphen. Liquid in glass thermometers. So what are liquid in glass thermometers? Liquid in glass thermometers. You've seen them before. This is a clinical thermometer, the one which is used for measuring body temperatures. Yeah, an analog one. Some of them nowadays, they are those that are modified that you find they are digital with digital scales. Yeah, the normal body temperature is approximately around 37 degrees Celsius. So this is a clinical thermometer, just a small temperature range. Then we have some ordinary thermometers. Here you've seen some of them in the laboratory. We have this one uses alcohol. There is colored alcohol, you can see. And then you can see by the color, it's reddish inside. The liquid inside is reddish. This red liquid is alcohol. Not necessarily ethanol. And alcohols are just a family of liquids. Yeah, we call them alcohols. So then here we have mercury. This is a mercury thermometer. You can see a mercury thread inside here. Yeah. So we want to explore liquid in glass thermometers. Examples of liquid in glass thermometers. I still forgot to include that, but you can always put it there for me. Yeah. Liquid in glass thermometers. Examples of liquid in glass thermometers. So they include clinical thermometers, like you've seen them. We have 6C's thermometer, what you call a maximum and minimum thermometer. This one was called the 6, just 6. Yeah, not 60, like some people say it is 6C's thermometer. 6C's thermometer. Yeah, a certain parent begat a child, and then certain parents too begat a child, and they decided to name, maybe firstborn was 1, secondborn was 2, this one was called the 6. Yeah, the 6th born was called the 6th. Yeah, like you hear some parents get children, firstborn is Monday, second one is Tuesday, Wednesday, just like that. Okay, examples of liquid in glass thermometers include clinical thermometers, 6C's thermometer. We have ordinary thermometers, the ordinary ones, the one that we use in the laboratory. Now, the thermometric property used in liquid in glass thermometers is the length of a liquid column in a capillary tube. Length of a liquid column in a capillary tube. We already looked at thermometric properties, and if you remember very well, one of the thermometric properties we talked about was the length of a liquid column. A liquid column, length of that liquid column in a capillary tube. The whole of this is the thermometric property. The thermometric substance used is that liquid. That liquid is the thermometric substance. But the thermometric property, you have to start from the length. So it's a length of a liquid column in a capillary tube. Always remember that when we talk about a thermometric property, we are talking about a physical quantity. So you have to talk about, for example, here it's length. It can be pressure, it can be volume, it can be resistance, like that. So we are saying that the thermometric liquids used are, we usually use alcohol or mercury. And actually, if you remember, just previously we looked at this, we said, what's the difference? There was this question here, they said, what is the difference? There's an alcohol thermometer, there's a mercury thermometer. Some of these parts will be yours for further discussion. All right. What are the advantages of mercury over alcohol as a thermometric liquid? A question. So advantages of mercury over alcohol as a thermometric liquid. Number one, mercury is commonly used because it is opaque and can easily be seen. It doesn't need even coloring. So by the color of mercury, so you can easily see where the meniscus ends, where the mercury thread ends, so you won't make errors. So mercury is opaque. Reason number one, it does not stick to the glass because of the greater cohesion than adhesion for mercury. So you always find that mercury gives better readings, more accurate readings when used than alcohol, because for it doesn't wet glass. That means the mercury column will have all the mercury there exists in that bore, in that given capillary tube. But if you have other liquids, those that have greater adhesion than cohesion, for them they can easily wet the glass. So the liquid column will not be containing all the mercury, all the liquid, that maybe all the alcohol that is in that tube, that capillary tube. Next, mercury doesn't vaporize easily. We know that mercury has a high boiling point. The boiling point of mercury is around the 357, something like that, degrees Celsius. So it means that it has a bigger advantage over alcohol. Alcohol boils at 78 degrees Celsius at standard atmospheric pressure, 78 degrees Celsius. But for mercury, we have 357, something like that. So you realize that mercury, for it has higher boiling point, and therefore it doesn't vaporize easily. So if someone wants to measure high temperatures using a liquid in glass thermometer, you will measure basically using a mercury in glass thermometer as compared to an alcohol in glass thermometer. Next, mercury is a better conductor of heat than alcohol since it is more sensitive to temperature. Hence, this should be hence, not since. English. Hence. I should have said hence. Yes. So mercury is a better conductor of heat than alcohol. Hence, it is more sensitive. It is more sensitive to temperature changes. Now, you know very well that if a substance is a better conductor, that means in case of any change, it will easily take up that heat and it will show the change in the temperature very, very fast. Please, I request you to replace this with the hence, not since, but hence. Hence, it is more sensitive to temperature changes. All right. Okay. On the other hand, what are the advantages of alcohol over mercury? Mercury, we've seen your advantages, but you also have disadvantages. Now, the advantages of alcohol over mercury are the disadvantages of mercury over alcohol. So just understand that. Alcohol has a lower freezing point than mercury. I like this. Mercury had a higher boiling point than alcohol, but now alcohol has a lower freezing point than mercury. It's around -115, -115 degrees Celsius. That's the freezing point of alcohol, and yet the freezing point of mercury is around -37. -37. Can you imagine? -37 degrees Celsius. That is the freezing point of mercury. So it means that if you want to measure maybe the temperature of a body, if the temperature is around -90 degrees Celsius, you can't use a mercury in glass thermometer, because by that temperature, mercury will already be a solid, but alcohol will still be a liquid. So alcohol has an advantage over mercury in that way. Next, alcohol is cheaper than mercury. Yeah, this should be very understood and well understood by everyone. And then we know that alcohol expands more than mercury. Please, not faster, but more. Now, the expansivity of mercury is about of alcohol. They say in practice for alcohol, the expansivity of alcohol is around 6 times that of mercury. An example is this: if you heat 1 cubic centimeter of mercury and you make it to expand so that you end up with 2 cubic centimeters of mercury. For alcohol, for it from 1 cubic centimeter, if you heat it through the same temperature change, for it you will end up with 6 cubic centimeters of mercury, of alcohol, not mercury. So in simple terms, the expansivity of alcohol is greater than that of mercury. Okay, enough of the comparison of the two. Now, what are the errors? What are the errors that result if you are taking readings, if you are taking temperature readings using a liquid in glass thermometer? We've looked at, for example, a clinical thermometer, using a 6C thermometer, using an ordinary thermometer. What are the errors that may result? Number one, the errors may result from the non-uniformity of the capillary tube. That capillary tube isn't necessarily uniform, so there may be non-uniformity, so it may lead to an error. Number two, the liquid in the stem may not be at the same temperature as that in the bulb. Now let me take you back a little bit. I show you what to mean by the bulb and the stem here. Look at this. You can clearly see that here, if you're looking at this alcohol thermometer, when you're placing this liquid in glass thermometer, if you are placing it in contact with the body, it's the bulb, this bulb, which has to be in contact with the body. But now, do you see that the liquid in the stem here may not exactly be at the same temperature as the liquid which is in the bulb? So for example, if you're measuring temperature at a point, even here for this one, which is using mercury here for the clinical thermometer, or even for this one. So the bulb is the one which is always put in contact with the object whose temperature is required. And as a result, we always end up with the liquid which is in the bore or in the tube or the stem being at a slightly lower temperature than the one which is in the bulb. So I talked about that. Okay, returning to our point. Number two, there is a gradual change in the zero reading due to the shrinkage after a long period of time. Now, after a long period of time, you realize that the stem, or basically the whole thermometer, will shrink. So the zero reading will have to shift its position. So this is an error that we will have. And then number four, there is what we call expansion and contraction of the glass. The glass expands and contracts. When you put it in a hot substance, it will expand. But remember, the readings will already be there. They won't cater for those expansions and contractions. And then lastly, we have what we call the parallax errors. Now, parallax errors, if you don't position your eye properly, if you're taking readings, you can end up with making what we call a parallax error. Parallax is the relative movement of two objects due to the movement of the observer. So in this case, you will have that, let me maybe make a simple illustration here. If this is our bore, if the mercury ends here, I'm assuming the mercury ends around here. Now, if you position your eye, you have to position it directly so that you take the direct reading like this from there. On the other hand, because of parallax, someone may read from here. when someone is reading from here, they may end up taking a wrong reading. Yeah, they end up taking a wrong reading, so they may read a temperature around here instead of reading the one around this point. So that is an error which results due to parallax. Parallax errors. Parallax is defined as the relative movement of two objects due to the movement of the observer. All right. Next, what now are the advantages of a liquid in glass thermometer? Yes, though there are errors, but there are also advantages. The first advantage, is we should understand that they are cheap. They are very cheap and portable. You can carry them. They are very portable. As compared to other thermometers, as we shall see, they are simple to use. For example, you just put, if you are using a clinical thermometer, there are places where they put when you go to the hospital. They can put under your tongue, they can put in the armpit, they can put in many places, and then they get your temperature. Very easy to use. And then it has direct readings, gives direct readings. Now someone is still thinking about the part where they put the thermometer. Okay. I don't know. There may be different parts. So advantages of a liquid in glass thermometer, we have basically these three. You can also add on more. The disadvantages, number one, it is fragile. That glass can easily break. And it's not very sensitive, because you know very well that glass is not a good conductor of heat. So it's not very sensitive, and it measures a small range of temperatures. Just imagine, if you're using alcohol, you can't go beyond 78 degrees Celsius, and you can't go below negative 115 degrees Celsius. If you're using mercury, you can't go below negative 37 degrees Celsius. You can't go above 350 something degrees Celsius. So those are disadvantages, that it measures a small range of temperatures. There are other thermometers like pyrometers that can measure even around 2000 degrees Celsius. Imagine 2000. This one is just ending on just hundreds. And because of the errors that we talked about, a liquid in glass thermometer is not very accurate. So it's not accurate. It's not very accurate. Now let's look at the constant volume gas thermometer. Constant volume gas thermometer. Like the name suggests, the volume has to be constant, and we have a gas. That means we are going to vary the pressure. So we are going to look at the variation of pressure at constant volume. So we can use that to determine the temperature. The pressure of a fixed mass of a gas at constant volume is a thermometric property used. The structure in diagram, even as if you are asked to explain in an exam, you're supposed to have this kind of diagram. For many of them, you find that here they draw some kind of a ruler. So you can have a ruler around here, a meter rule or any ruler. So that's in many books they indicate it. Yeah, around here. So you find a meter rule, they indicate. I won't put everything. So in practice, I want you to know how it operates. Then I will show you a simple demonstration. First, put these off. Okay, fine. Sorry. Now, a constant volume gas thermometer has a gas. So we have here a gas bulb. They usually talk about air, though in more real terms they use hydrogen. But here we have a gas. Now we know what happens, that when you heat a gas, the pressure will increase and the volume will increase. So a gas expands. It expands. So we have a gas in a glass bulb. And then look at this. The dead space consists of a very tiny capillary tube. There is a tube, a small tube, but that small tube is what we call the dead space. Connecting to a tube B, there is a tube B here. Inside here we have mercury. There is mercury here, you can see, it's labeled. And then we have what we call the constant volume mark. So there is that mark there. We have to have a mark around here, around this point here. We mark it properly. We mark this point and observe it properly. So that every time the mercury ends here, it means that we know that the volume inside this glass bulb is constant. Otherwise, if the pressure increases here and then it pushes because of the expansion, when you put this glass bulb in a hot substance or a liquid, it means that it will push this mercury into the rubber tubing. It has to be flexible. Now, let me first talk about the parts. So we have a glass bulb, like you have said before, the dead space, constant volume mark. We have the two tubes B and C connected to a rubber tubing. Now, the whole combination has mercury in it. So there is mercury inside here. There is mercury inside here. The other end of tube C has to be open so that atmospheric pressure acts on it from this point here. So, you know very well that at this point you can measure the pressure of this gas here. The pressure of this gas is simply, you know very well that here atmospheric pressure is acting. And now if there is this height difference here, it means that the pressure, because the gas exerts its pressure at this point, while the atmospheric pressure is exerted from this point, or the air pressure. So it means that since the gas pressure here, the gas has pushed the mercury in limb C to have that height, positive height, it means that the pressure here is going to be, the pressure there is going to be, I didn't want a highlighter. The pressure is going to be simply, you get atmospheric pressure and then you plus or you add that height. And remember, whatever you get will be in millimeters of mercury or centimeters of mercury or meters of mercury. But basically, observe that this is the height, that difference in the menisci levels. So the meniscus ends here for this point, the reference, and then on the other hand, the meniscus ends up here. So the height at the difference is what you're calling the H. Now, because this one has pushed, the air pushed the atmospheric pressure backwards, upwards actually, it means that it is greater. So we're going to have pressure equals to H plus small h, like that. Please observe that strictly you have to write this as a rubber tubing. It's not a U-tube, it's a rubber tubing. You either call it a rubber tubing or you call it a flexible tube. It has to be flexible for reasons which we are going to see very soon in an animation. Not really an animation, but an experimental video. Okay. Let me first clear these annotations so that you may know. If you are to draw, this is what I expect you to draw. First, remove everything that is not wanted. Yes. Don't want this, don't want this, don't want this. Even you don't want you. Good. All right. Now, my point is, are you able to draw that? You can always include a meter rule in the middle here, but I just didn't include it. Now, how does it work? Let me first show you a video. some video here so you can see exactly how it works. Look. You can see that here we have warm water. This is our bulb here. You can see the dead space. They didn't complete the whole of it. This was in a laboratory. So here we have a bulb, the glass bulb. So you see the flexible tube is down here. You can't see it properly, but you see it's down here. Yes, the flexible tube starts from the rubber tubing. Not really rubber tubing, but the rubber tube is here. So there is a tube here, this side, and there is another tube. This is what we call the B, just because it is rotated. It's rotated. Now, when you put this glass bulb in a hot substance, what will happen is that the pressure here, the gas will expand, and so its pressure will increase, and so it will push. You see the reference level? This is where there is zero. Where there is a zero mark, that's the reference level. That's the reference level here. So when the gas expands, so it will push the mercury downwards in the right limb, or the tube C, B, this was B according to our diagram, and then in tube C it will rise. And so when it rises, what we do, that's when we are fully immersed this bulb into the substance whose temperature is required. What will happen is that we will have to raise, we're going to raise this tube, which we call the tube C, until the level of the mercury in tube B is restored to the original reference level, or the constant volume mark level. Okay, now let me repeat this and then I talk through that you may understand exactly what I'm talking about. Here we have warm water, and then we found a way of raising it. So when you raise it, please observe that we are having the reference level here. We have a reference level, or what we call the constant volume mark. Observe that when the water, now the hot water, gets into contact and with the glass bulb, which is fully immersed, do you see that the mercury in our right limb, right tube, has now been depressed because of the pressure which increased? So what we're going to do is that for us, the other one rose. From this point it rose up, this one came down. So what we're going to do is that we are going to raise this side here. We raise it a little, raise it, you raise it until it is restored. The mercury in our tube, which we call the tube B, until it is restored to the original mark. Now, once we do that, the difference between this point and the other point is what we call the H. The H. It ended very fast. So let me just take it a little, so you see exactly the difference that I was talking about. Yeah. Okay. I hope you saw that. Maybe just to take you back to the diagram. Yeah. This is the constant volume mark. The reference level is here. So the difference between the two is what we call H. All right. Now, we say that the thermometric property used is the pressure of a fixed mass of a gas at constant volume. So to measure the temperature on a Celsius scale, the glass bulb is immersed in a body whose temperature is required. You see, there are disadvantages, as we shall see later, because for a constant volume gas thermometer, it requires measuring a temperature of a body when you can immerse the whole bulb in that body. So preferably for liquids and gases, it's easy. So time is allowed for the gas in the bulb to acquire the temperature of the body. Next, The flexible tube, or what we call the rubber tube, is adjusted until the level of the mercury is brought back to the reference mark. Already you saw that. And the difference H in the mercury levels in the two limbs is measured and recorded. That difference H has to be measured and recorded. Please, you write down these steps just the way I've given them to you. Very easy. Next, you can always pause. If you find that the video was fast, just pause and then write and you continue playing. So the pressure which is P theta is going to be H. This capital H represents atmospheric pressure plus or minus small h, where capital H is atmospheric pressure. Now, why do we say plus or minus? Plus or minus, we put plus or minus bearing in mind that the pressure of the gas can be less or equal, or less or greater than the atmospheric pressure. But in most cases, we write P theta equals to H plus small h. So the procedure is repeated when the bulb is immersed in steam from boiling water to get P100. So when you immerse in boiling water, you get P100. P100 is simply going to be, P100 is going to be, we are going to write P100 as, you can say that P100 equals to, it's going to be our atmospheric pressure plus height, the height at 100, like this. Then P theta, the pressure at that unknown temperature is going to be atmospheric pressure plus the height, the difference in the heights in the levels of the two menisci, which is going to be H theta. Then when immersed in pure melting ice, we get P naught. P naught is going to be H minus, this is plus. All cases we have plus. H naught. Then observe something. We know that on a Celsius scale, remember what we wrote previously. We said that on a Celsius scale, if you want to determine the unknown temperature on a Celsius scale, you say theta. You say theta equals to x theta minus x naught over x 100 minus x naught. So for our case, the x is known, the thermometric property is known. So we're going to say P theta here minus P naught. So P theta can be written as capital H plus small h theta minus P naught, which is going to be capital H plus H naught over P100, that is H plus small h 100, and minus P naught is still capital H plus small h naught, like that. Then the whole thing we multiply by 100. I didn't leave the space. Yeah, but you can see what I'm doing here. So now when you simplify this part, you're going to end up with theta equals to H. We can write H. Oh, let me rub this a little bit. So here we have, okay. We have H theta minus H naught over H 100 minus H naught, and the whole thing we multiply by 100 degrees Celsius. So, in other words, what I want you to know is that if you don't use the formula for constant volume gas thermometer, if you don't use the formula, this one here, theta equals to P theta minus P naught over P100 minus P naught times 100 degrees Celsius, because here it means that you have to first calculate the pressures. You can just use theta equals to, you take H theta minus H naught over H 100 minus H naught, and the whole thing you multiply by 100 degrees Celsius. Exactly. So that makes life easy for you. Now, inaccuracies will always arise. They will arise. Inaccuracies here will arise from basically the gas, not these points, please, not them, that the gas in the dead space may not exactly be at the same temperature as that of the gas in the bulb. The gas in the bulb may be at a higher temperature than that in the dead space. So that may be a source of error. Number two, you know that the bulb, the glass bulb, being glass, it can expand and contract. So the expansion and contraction of the bulb. And number three, capillary effects at the mercury surfaces. You know that mercury undergoes capillary depressions. So we will have capillary effects at the mercury surfaces. So those are the three sources of error that may arise. In when you are taking. These may be the sources of errors. These may be the sources of errors that you will end up in the readings. You end up with in the readings taken using a constant volume gas thermometer. So how do you rectify them? So these errors can be minimized. Roman 1, you can make the dead space very narrow so that as little gas as possible is present there. Number 2, you use perspex. Instead of using glass, use perspex. You know that perspex has a low value of expansivity. It doesn't expand a lot. And then on the other hand, you make the glass tubes wider. The glass tubes, make them wider. Okay. When you make them wider, you're going to minimize the capillary depression. You minimize the capillary depression. So I try to arrange these corrections according to the error sources of errors. Okay. Now, what are the advantages of a constant volume gas thermometer? What are the advantages? Number 1, it is very accurate. Very accurate. Yeah, actually, it's the standard when we are calibrating even other thermometers. We always refer to this one. It's very accurate. Number 2, it measures a wide range of temperatures. Yes, it measures a wide range of temperatures as compared to liquid in glass thermometers. And it's very sensitive. Very sensitive. And then it agrees with the Kelvin scale. Yeah. Now, that's even what makes it very accurate. When you're using, even on the Celsius scale, the values you get on the Celsius scale, even when you use the lower fixed point and the upper fixed point, if you decide to use the triple point to establish the Kelvin scale, still you will end up with the values agreeing for a constant volume gas thermometer. So, the constant volume gas thermometer is a very good one. Now, what are the disadvantages? Number 1, it's bulky, like you've seen. It's bulky. For a liquid in glass thermometer, it's just a matter of holding something very small. But now here, it's bulky. It cannot be used to measure rapidly changing temperatures. So it doesn't really respond as fast as possible. It's not so quick. So Rapidly changing temperatures can be measured using a volume gas thermometer. And next, it has no direct readings, so you have to first calculate. And it cannot measure temperatures at a point. Please note this, it cannot measure temperatures at a point. Remember, the other one is just a glass tube like this, the glass bulb. Then if you want to measure temperature at this point, so how would you place it, immerse it in that point? It becomes hard, because for it basically operates on the principle of immersion. You immerse and immerse. Okay, I'm going to actually stop it there. We have looked at basically two types of thermometers here, the liquid in glass thermometers and a constant volume gas thermometer. Kindly, I request you to take time and analyze the details of these thermometers, analyze them and understand them, and also try to find out how do we determine the upper fixed point. Yes, upper fixed point, the steam point. You learned that in O-level using a hypsometer. You can easily refer to AF Abbott. It has those things, and even other books. You can also go ahead and find out how we determine the lower fixed point. The lower fixed point, what we call the IC point. Yes, thank you very much. I sign out. Let's meet in B003, the third lesson of section B. And that's the thermal properties of matter. Thank you very much. May God bless you all. Bye-bye.